Hi everyone. So in today's lecture, we are going to see efficiency and throughput of Aloha. Okay. So let me just revise you that what we have seen. We have seen that what does this efficiency mean, what does this throughput mean, and these two are basically equal if we are measuring throughput in packets per slot or packets per transmission time. So slot also mean transmission time. Right? So probability of slot not getting wasted is also equal to the efficiency. That's what we have seen. But anyway, let me just quickly revise that what we have seen, right? Okay, so Aloha efficiency, that's what we want to talk about in this lecture. And then this can be analyzed in two ways. One case is that when there are very large number of stations, or the second case is that when there are finite number of stations. Okay, so let's just see the case one first. In the case one, we will be applying something called as Poisson distribution. In the case two, we will be applying something called as binomial distribution. Okay, that's the only difference. Let's just see the case one first. So to formulate the performance of multiple access network, we need a mathematical model, right? And then we have said that, okay, let's just define a random variable X, which is the number of times, number of frames in one transmission time. So which means number of frames in slotted Aloha, we will say number of frames in one slot, right? So let's just say that expectation of X is G. So what is G here? Like we have already seen all of this. That's why I'm quickly just revising you. What is G here? G is average number of frames generated by system in one transmission time or in one slot. Okay. So suppose that I say that X is number of frames in one slot, then what is the probability that exactly one frame get transmitted in one slot? So for that, we need Poisson distribution. So let me quickly recap you Poisson distribution. Already we have seen these things in the last lecture, but still I'm just quickly revising you. So we say that if X is a random variable, which is a Poisson random variable, then probability of X being K is just like this, right? So what does this X equal to K mean? That we say that in a certain time period, probability of K events happening, right? Probability of K events happening. Right? Okay. And what is a lambda here? Lambda is expectation of X. Lambda is expectation of X in that certain time period, right? So for example, I gave you the examples also. Let's suppose on average, there are 2 accidents per day, which means lambda is given to you as 2. Then they're asking, what is the probability that 4 accidents in a given day, which means they're asking X equal to 4. Then you can apply the formula, which is e power minus lambda into lambda power K upon lambda factorial, right? Sorry, K factorial. So this is the formula for Poisson distribution. Now, if you apply this, then it will be e power minus 2 into 2 power. What is the value of K? You are looking for K equal to 4, right? Into 2 power 4 upon 4 factorial. So this is the probability of 4 accidents in a given day, right? If on average there are 2 accidents per day, then 4 accidents in any given day, this is the probability, right? Okay. Now let's just move to the next slide. So as you can see, the answer is this, right? Already we have seen all of this in the last lecture. Now let's just quickly calculate this. On average, there are 2 accidents per day. Then what does this mean? That lambda is given to you 2. Then what is the probability that 4 accidents in they are asking in 2 days? So tell me, should you be modifying the lambda if the time frame is different? Right? So what they're asking here is different from what they have given. I mean, they're asking for 2 days. So what is the modified lambda? In 2 days, there will be 4 accidents, right? It will be 4. So hence, what is the probability of X being 4? Now you can apply the formula, which is e power minus lambda, e power minus 2 into lambda power K upon K factorial. So something like this, right? So here, sorry, this lambda is 4, right? Here the lambda is now 4. Okay. Yeah, this is the answer. And now just this last question on the recap, that if they have given the average that there are 2 accidents in 2 days, Then what is the probability for 2 accidents in one day? Okay, here the modified mean is 1. Is this? On average, there are 2 accidents in one day. So how many accidents will be there in 2 days? In 2 days, there will be 4 accidents, right? Yeah. Okay. Coming to this, on average, there are 2 accidents in 2 days. So lambda given is 2, but this is given for 2 days, and they are having something for 1 day. So modified lambda will be, yeah. So it means you can calculate this probability, which is e power minus lambda into lambda power k upon k factorial. So e power minus lambda means e power minus 2 into 2 power, e power minus 1, because lambda modified lambda is 1, 1 power something which is 2 upon 2 factorial. So this is your answer, right? I mean, I hope you can calculate all of this. We have already done this in the last lecture. Okay. So this is the question that we were interested in. Okay. Now, what is the probability of transmitting? If I just ask you what is the probability of transmitting k frames in one transmission time? If G is the average number of frames generated by the system in one transmission time, so this one transmission time and one transmission time here are same. So this lambda given, this G is nothing but the lambda of the mean, right? Which is same. So you can directly find out probability of X being K is e power minus lambda into lambda power k upon k factorial. So this lambda given is G. So that's the only change here, k factorial, right? So e power minus G into G power k, right, upon k factorial. Now, if I just ask you, what is this P0? P0 means probability of X being 0, which means that exactly 0 frames means that no one is transmitting in that given slot. What is this probability? E power minus G, right? If k value is 0, then you will get e power minus G. What is the probability that exactly one station is transmitting in given slot? Exactly one station transmitting in given slot. Yeah. So this probability can also be calculated very easily. This is e power minus G into G, right? Or G into e power minus G, whatever you want to say. G into e power minus G. Do you recall that this probability is very interesting to us? This probability is same as something called as efficiency. This probability is same as throughput if I'm measuring throughput in packets per slot, right? So this particular probability is very much important. So I will come to that in just a minute. Already we have seen all of this, right? Still, I'm just revising. So the consider slotted Aloha, we can say that slot is not wasted whenever there is only one station transmit, right? Exactly one station transmit, then the slot is not wasted. No one is transmitting, slot will be wasted. Multiple transmitting, slot will be wasted, right? Exactly one transmitting, slot is not wasted, right? So we are saying that probability of slot not wasted, probability of slot not wasted is same as exactly one station is transmitting, is same as efficiency, is same as throughput. If we are measuring the throughput in, can anyone tell me? Packets per slot, right? Packets per slot. So we have seen all of this. So let me just quickly recap you that suppose that probability that slot is not wasted or exactly one is transmitting. Let's suppose this probability is 0.2 or exactly one is transmitting. Let's suppose this probability is 0.2. Okay, assume, right? Then what does this mean? It means that this is 2 upon 10, right? It means that you can say that out of 10 slots, okay, these are the total slots. You can say these are the total slots. And this is, you can say this is basically the slots not wasted, right? So out of 10 slots, how many slots are not wasted? 2 slots are not wasted, right? So this probability means that out of 10 slots, 2 slots are not wasted. Then what does this mean? It means that out of 10 slots, how many packets you are sending out of 10 slots? If 2 slots are not wasted, then in one slot you can only send 1 packet. So you are actually sending 2 packets, right? So you are sending 2 packets in 10 slots. 2 packets in 10 slots. Which means packets per slot will be 2 upon 10. And this is nothing but throughput. So basically throughput in packets per slot is 2 upon 10. So this probability of X being 1, if you recall, that probability of X being 1 was G into e power minus G, right? This is same as throughput. Okay. So probability of X being 1, which is G into e power minus G. Okay. This is same as throughput if you are measuring throughput in packets per slot. Okay. Let me know if this revision is fine to everyone. I mean, these things we have already stabilized in very good detail in the last lecture, right? Okay. We have spent just 2-3 hours just to make sure that you have understood these things, right? Okay. I hope that is fine. Now, yeah, by the way, like if I just ask you what is the throughput in this slotted Aloha, then what is your answer? Throughput in slotted Aloha? No, Siddharth, what no, you are telling 0.386. Is this the throughput in slotted Aloha? No, the throughput is this much, right? This is the throughput. Yeah. Yes. So whatever you are telling is basically the maximum throughput, right? But the throughput is this much. Okay. So this is the throughput in slotted Aloha. Interestingly, if you I mean check any other resource, I mean any other resource in the sense like I mean in most of the resources or most of the gate coachings in those, they will just tell the throughput in slotted Aloha is this much, right? Okay, forget about this that they will not then will they be telling that okay this is same as the probability of X being 1. Forget about this, they will not be even telling this, and apart from that they will interestingly they will not even tell that what is the unit of this throughput. Okay, they will just say the throughput in slotted Aloha this, and they will not be even knowing that okay this throughput means that we are measuring in packets per slot, right? Has anyone seen or anyone studied this topic from anywhere else before? So they will just say the throughput of the slotted Aloha is this much, right? And they will not even tell the unit. That's very interesting. Okay, they will not even tell the unit. They will just say throughput is this much. Okay, you forget about this relation. Anyway, so throughput in slotted Aloha is this if we are measuring the throughput in packets per slot. Okay. So suppose the slot means the transmission time, right? Suppose this transmission time is 10 millisecond and the packet is basically, let's suppose 200 bytes. And if I just ask you, can you tell me that, I mean, if I just say that throughput is something, and which is like I will tell that okay throughput, let's suppose 0.2, okay, 0.23, let's suppose. And if I say that okay the packet size is this and the slot size is this, can you convert this throughput which is in the packet per slot to maybe kbps? Can you convert? Definitely, right? So suppose for example I say that throughput is, anyway we will be having the questions, okay, throughput is, let's suppose 0.2. Suppose I say throughput is 0.2 and which I am saying in packets per slot. Okay, packets per slot. Now this packet size is also given to you, let's suppose. Okay, let's suppose this size is 200 bytes, and suppose slot length or the transmission time, okay, which the slot length and transmission time are same in the Aloha. That's what we have seen. So the transmission time is given to you, let's suppose, is 1 millisecond. Okay, then can you tell me what is the throughput in kbps? Just tell me. See, this is 0.2 packets you are sending in 1 millisecond. So in 1 second, how many packets you will be sending? In 1 second, you will be sending 0.2 into 10 to the power 3 packets. Is this okay to everyone? So this is packet per second, but I want in the, can you convert, which means basically I'm saying here is that if, let me go to the next page and solve this question. In 0 point or in 1 millisecond, you are sending 0.2 packets, right? In 1 second, how many packets you will be sending? You will be sending 0.2 into 10 to the power 3 packets. Obviously, you just multiply 10 to the power 3 both sides, and then you will be getting this. Obviously, you will be sending more packets in 1 second, right? And now, if I ask you that in 1 second, how many bytes you are sending, you will say into 10 to the power 3 into. So one packet is 200 bytes. So 200 bytes, right? Bytes. These many bytes you are sending. So this is bytes per second, but I want in kbps. So you can just omit this, and then you will say it will be 40 kbps, right? It will be, yeah, it is 40 kbps. So finally the throughput is coming out to be 40 kbps. Okay. So that's how you can definitely convert given throughput. I mean, they will not tell that it is in packets per slot. That's what you need to know. I mean, let's suppose they say the question is like this. They will not say the throughput. They will say the probability. Okay. Let's suppose the question is like this. They say the probability of sending exactly one frame in a given slot is, let's suppose this is 0.2. Okay. Then tell me, will anything change here? Any of this thing change? Any of the calculation will change, or everything will remain same? I mean, in this calculation, instead of giving the throughput, they say that, okay, the probability is 0.2 of x equal to 1. Probability of x equal to 1 is given 0.2. Doesn't it directly mean that they have given the throughput 0.2 in the packets per slot? Right? So they have given the probability of x being 1, which is 0.2. Doesn't it same as the throughput? Can't I directly say the throughput is 0.2 in the packets per slot? Right? So if they give you this could be very easy question. They will just give something like this, and then they will ask the throughput in kbps. And if you do not have the good understanding, like, you will not be able to solve this question. Otherwise, this question is very straightforward. Right? So this probability of sending exactly one frame is same as the throughput, which is in the packets per slot. And then they're asking the throughput in kbps. So this is your answer. Okay. Okay. Now the throughput of slotted Aloha is this much, right? I will, by default, it basically means that it is in the packet per slot. Okay. I will not again and again saying that it is in the packets per slot. It is packets per slot you are sending, which means these many packets you are sending per slot. Is this fine to everyone? If someone asks you what is the maximum throughput, so throughput of the slotted Aloha is this much. Okay. So this particular, I can say, slide is very, very important. Okay. So maybe I can write this line here also. Okay. So let's just put this as a heading, that what is the throughput of slotted Aloha. So what is the throughput of slotted Aloha? It is G into e power minus G. Is this fine to everyone? This is the throughput of slotted Aloha, right? Is this the maximum throughput? No. This throughput is in kbps? No. This throughput is in packets per slot, right? Unit here is packets per transmission time, or you can say packets per slot, because slot size is same as the transmission time. Okay, cool. So I hope you understood this. Now, this is a throughput. Okay. Now, if you want the maximum throughput, then for what value of G you are getting the maximum throughput, you need to just differentiate it to get 0, then G is coming out to be 1. Okay. It means that maximum throughput, if you plug in the G value to be 1 here, the maximum throughput is coming out to be 1 upon E. Is this fine? And also, is this logical that if on G, what is G? On average, how many packets you are generating in one transmission time? If let's suppose on average system is generating just one frame in one transmission time, then G will be 1, and then it is maximum, right? If system is generating more than 1 or lesser than 1, then it will be a problem. Okay, I have also shown you the graph, if you remember. Then graph will look something like this. See. See, all of this discussion we have already done, right? Yeah. So this is the graph. Okay, understood. That if you are increasing G, then the throughput is decreasing. If you are having lesser G, then also throughput is less. But if G equal to 1, then throughput is maximum. Which means if system is also generating one frame on average, okay, one frame per slot, then it is the best case, right? So why throughput is not 1 here? I mean, if system is generating just 1 frame per slot, then why we are not always able to successfully send it? Can anyone guess it? If system is also generating just one frame per slot, then what is the problem? Why we are not directly sending it? Because this is average, right? I mean, G is average, which means sometimes system will generate two frames, sometimes system will generate 0, sometimes just 1, sometimes just 2, sometimes 3, and so on, right? So this is average. So here no successful transmission, this slot getting wasted, this slot is successful, this slot getting wasted, right? So even though G is 1, it means that this is average 1, which means on average system is sending 1. It doesn't mean that in all the slots system is sending just 1. If in all the slots system is sending 1, then what is the throughput? I mean, if obviously that is not possible, but let's suppose system is just sending 1, okay, in all the slots, then the throughput will be maximum. It will be 1, right? Yeah. But in Aloha, that is not possible, right? So the maximum throughput we can get is basically 0.368. Okay. So we have solved this question. If you remember, let's just quickly, maybe, should I solve this again, or I can go to the next slide? Tell me. Maybe I can just solve it within a minute. So what they are saying is that what fraction of slot goes empty in this system? So they are saying that that what is the probability of X being 0, right? Slot going empty. Then if you remember, it was e power minus G, right? I mean, you can plug in the formula, lambda power K upon K factorial. So lambda is G, K is 0. If you plug it, that will be e power minus G. So what fraction of slots? So basically they are asking fraction of slots means they're asking that out of total slots, how many are empty, which is probability of X being 0. So this is your answer, right? Now, what fraction of slot goes empty when system is operating its maximum throughput? Then at that time, G is, do you remember what is G? If system is operating its maximum throughput, then G must be 1. So it will be 1 upon E at that time, right? Yeah. So in general, it is e power minus G, the probability of X being 0. But if system is operating at its maximum throughput, then it is 1 upon E. Now let's just solve this question. A slotted Aloha system has packets, both new and transmission, arriving at the rate of 50 per second. Yeah, we have already solved this, but okay, let's just quickly solve this also. So suppose they are saying that they're arriving at the rate of 50 per second. Packets take 40 milliseconds to transmit, right? So what is the transmission time here? 40 milliseconds. Okay, we have solved this question in the last class, so that's why I'm doing it little quickly. Now you tell me what is the value of G, packets per slot, on average. So if you are sending 50 packets per second, 50 packets in 1 second, in how many seconds we are interested to know for the G? We are interested to know in 40 milliseconds what you are doing, right? So in 1 second, if you are doing 50 packets, in 1 millisecond, you will be definitely doing lesser. So in 1 millisecond, you will be doing this much, right? In 40 millisecond, you will be sending this much. So this is your G, right? This is your G. Everyone understood this, that how we are calculating G from this given information? Let me know if there is any doubt. I can explain this again. Okay, so G is basically how much you are sending on an average in one slot, right? So in one slot, you are sending this much. If you are sending, let's suppose 50 packets per second, then in one slot, you are sending these many packets. So if you calculate it, then G is coming out to be 2 packets, right? This is coming out to be 2, right? Okay. Now they're asking the next question is that, what is the probability of success during a slot? So probability of success means what? Probability of X being 1. Okay. So if G is 2, then you can calculate it G into e power minus G, right? Which is same as throughput, and these things we have already seen. So this will be 2 into e power minus 2, right? Okay. Now they're asking what is the average number of slots per successful transmission? What does this mean? It means if the probability of success is given to you, okay, I mean, which means out of, let's suppose, some slots that, this is the fraction of slot that gets successful. Okay, if the probability of success is this, then how many slots will be needed to make sure that there is at least one, there is basically just one success? This will be 1 upon P, right? We have seen this. Okay, in the last class also we have seen this. It will be 1 upon P, right? Okay, so if the probability of success is P, then 1 upon P is the expected number of trials you need to get the success, right? So 1 upon P will be the expected number of slots to get one transmission. If you want to send 10, if you want to send 10 packets, okay, then how many slots you will need? Then you need 3.69 into 10, which means you need on average 36.9 slots, which means if the transmission time is also given, then you can say that 36.9 into 40 milliseconds you need if any station wants to transmit 10 packets, right? If any station wants to transmit 10 packets, then this is the time on average that station will be needing. See, what is the transmission delay? 40 millisecond. Okay. In idealistic case, it could be just for one packet 40 millisecond into 10. Okay, just like this. Okay, for the 10 packets. But here it is not like this. I mean, here you need to basically multiply by 3.69, because just to send one packet you are wasting 3.69. I mean, you are taking 3.69 total slots on average. Okay. Anyway, these things we have seen. Now let's just move to the next question, which is a new question here, which we have not seen in the last class. Okay. Have we seen this or we have not seen this? Okay, so anyway, let's just solve this. So suppose you measure a slotted Aloha channel and determine that 10% of the slots are ideal. Then what does this mean? That probability of X being 0, can you tell me? Have they not given probability of X being 0? Yes. So what is the probability of X being 0? By looking at this line, can you tell me what is the probability of X being 0? This is 0.1, isn't it? Right? This is 0.1, because that's what they are saying. The 10% of slots are ideal, right? Which is, if you remember, it was e power minus G. So e power minus G is given to you, which means indirectly G is given. So now they're asking what is the channel load. So can you not calculate it? I think we can do it, right? So e power minus G is this. Then if you take the log and all, it is coming out to be, okay, I'm not calculating it, but yeah, if e power minus G is 0.1, then G is coming out to be 2.3. Okay. So how we can calculate? You can just do e power G equal to 1 upon 10. So e power G is 10. Take the log both side, log base E maybe, right? And log base e power G equal to log base E 10. Then this is 2.3. Okay. Anyway. So what is the system throughput in packets per slot? So now they're asking system throughputs in packet per slot. That means they're asking which quantity? G into e power minus G. So if you know G, which is 2.3, if you know e power minus G, which is 0.1, right? Yeah, this is 0.1. So that's how you're going to calculate this. Okay, it will be 0.23. This is the system throughput in packets per slot. Now, is the channel overloaded? Overloaded, underloaded means, actually it means that if G is greater than 1, it is overloaded. If G is greater than 1, it means you are transmitting on an average, you are transmitting in per slot many things. So this area is overloaded, this area is underloaded. Okay, so tell me if G is greater than 1 or not. Since G is greater than 1, then we will say it is overloaded. Okay, I mean, this is just one theoretical term. If G is greater than 1, then we say system is overloaded. Okay, so have you understood this question? Everything about this question, right? Now let's solve many more questions. Okay. Okay. Before that, maybe I can just ask you that what is the probability of transmitting k frames in the entire vulnerable time? Here in the slotted Aloha, the vulnerable time is TT, which means this is the time that that is basically having the probability of collision, right? Which means that if someone is sending, I think we talked about it, right? See. See here. So vulnerable time for the slotted Aloha. Now, if you see here, then can you tell me that at what time any station can send? Can any station can send in between of this? In between of the slot? No, right? So they can only send either at the beginning or at the end. I mean, beginning of the slots, right? So they can only send at this T. Now, if two stations wants to send, can one of the stations send at T and can another station send later on this T? No, right? So both has to send at T. Now let's suppose there is a collision. So what is the next time they will be trying? At least they will be trying after this vulnerable time, right? I mean, or basically they cannot try in between. So if there is a collision here, then anyway this particular whole slot is wasted, right? Or just this time is wasted. Tell me, if there is a collision at this time T, then is just 0.1 second or 0.01 second are wasted, or the whole slot is wasted? Whole slot is wasted, right? So this is called vulnerable time. Basically, it means that the time in which there is a probability of collision, okay, and which is basically eventually getting wasted if there is a collision. So here you are wasting one slot if there is a collision, right? So that's why here in the slotted Aloha, the vulnerable time is TT. In the pure Aloha, where there is no slots, the vulnerable time is 2TT. Now this G is defined just for TT, okay, which means it is not like that this G we are defining for slotted Aloha separately, for pure Aloha separately. No, okay, G is defined just for TT, which means lambda is given to you in this TT time. Now, if they ask you the probability of transmitting k frames, then what is this probability? X equal to k is e power minus lambda into lambda power k upon k factorial. Now tell me what is the value of lambda here? Lambda is G, right? Lambda is G power k upon k factorial. So this is the probability in slotted Aloha. But interestingly, this lambda here, we need to modify in the pure Aloha, okay? So modified lambda will be, since they're asking for the vulnerable time, which is 2 TT, probability of transmitting k frames in the entire vulnerable time, they're asking for the 2 TT time. So given lambda is for TT time, and now you want to calculate something for 2 TT time. So what is the modified lambda? It will be 2G, right? Which means they are saying in TT time on average G transmission. So in 2 TT time, there will be 2G transmissions, right? So that's why in the pure Aloha, instead of G, we use 2G. So e power minus lambda minus 2G basically into 2G power k upon k factorial. Okay. So don't worry about much of the derivation here. It is basically to the core, it is very complicated. Okay. To the core, it is not that easy in the pure Aloha. So there are, I mean, even in the any of the textbook, these kind of derivations are skipped. Okay. So I'm just trying to give you some intuition from here. Okay. So now you tell me what is the throughput in pure Aloha. So just remember that in pure Aloha, instead of G, whenever we are using G in the Aloha, in the pure Aloha, we use 2G here. So what is the throughput? Throughput means probability of X being 1. So now can you tell me what is the throughput here? Do you remember throughput in slotted Aloha? It was e power G into e power minus G, right? This is throughput in slotted Aloha. Do you remember this? Now, let's just see what could be the throughput in pure Aloha. So it is basically, if you put this K as 1, right? This is the throughput, sorry, into 2G. This is the throughput in the slotted, in the pure Aloha. Okay. Is this fine to everyone? Okay. G into e power minus 2G. Was just 1 second. Okay. So, So, okay, let me just tell you. So basically, this is basically this throughput we are having here is per 2T time. Okay. Okay. Number of, this is the unit here is that packets per 2T time. Anyway, you don't need to do all of this. I will just tell you the direct formula here. So if you want the throughput of pure Aloha in TT time, then you will just divide by 2. Okay, this is per 2T time. So you can say the throughput of pure Aloha. Yes, Akash, that is correct. So Akash is also saying that it is basically number of frames per 2T time. Yeah. Okay, because here the time frame was different, right? So earlier the time frame was TT, but here the time frame is different. So this is number of frames in per 2TT time. That is correct. Okay, here the time frame is different. But let's suppose I want the throughput of pure Aloha in packets per transmission time only. Then it will be just G into e power minus 2G. I mean, you will divide by 2. Okay, you will divide by 2. This 2 will get cancelled out. Okay, here the time frame was different. And now if you want to resettle in the old time frame, which means in the TT time, then you will say that this is the throughput of pure Aloha. What is the throughput of slotted Aloha? It was G into e power minus G. Okay, both are in packets per transmission time or packets per slot, right? Okay, so maybe with the questions it will be more clear. So let's just move to the questions directly. Consider the slotted Aloha. What is the probability that no station transmit in entire vulnerable time, which means probability of X being 0? Do you remember? It was e power minus G only, right? Yeah, it was e power minus G. And now the slotted Aloha only, that exactly 1 frame. Then we have G into e power minus G, right? Now pure Aloha, an entire vulnerable time, which means 2TT time. Okay, here this is 2TT time. So you will consider, I mean, the same formula you will consider, which means probability of X being K is the position distribution lambda power K into e power minus lambda upon K factorial. The same thing you will consider, but here you will consider this lambda in 2TT frame. So lambda is basically 2G. That's the only difference. Now, can you tell me the probability of X being 0? Okay, in the entire vulnerable time, what is the probability that there is no one is transmitting in the 2TT time? Then you will say that here it is K value 0, right? So it is minus lambda. So it is e power minus lambda only. So it means e power minus 2G. Is this fine to everyone? Right? Now, okay, so e power minus 2G. This is now, let's suppose I ask you that this is pure Aloha only in the entire vulnerable time, exactly 1 frame. Okay, in the entire vulnerable time, exactly 1 frame. So again, this lambda here is 2G. Okay, so see, the same question they can all ask in saying slotted Aloha, and instead of saying entire vulnerable time, what will they say? I mean, if the answer they want the same 2TT time, right? So they can also say 2TT time, which and they can say slotted Aloha. Then also answers will be same, because then also you need to modify the lambda, which will be 2G. So if they are saying slotted Aloha and entire bundleable time, then do you need to modify the lambda? No, right? No. If they are saying entire bundleable time in the slotted Aloha, this is on the same time frame, which means that in the bundleable time here is just TT. So you do not need to modify the lambda. But if they say pure Aloha and they say this entire bundleable time, then do you need to modify the lambda? Then yes, right? So lambda will be in the entire bundleable time, the lambda will be 2G. Okay, lambda will be 2G. So which means e power minus lambda into lambda power k upon k factorial. So x equal to 1 is means e power minus 2G into 2G, right? This is probability of x being 1, which is throughput in entire bundleable time. Okay, and throughput per transmission time will be this much. You need to cross this two. So for example, if I just ask you slotted Aloha, okay, take 2TT time. Okay, so if I just ask you what is the probability that no one transmit then what is this probability? See, lambda here will be 2G, isn't it? Because in 2TT time they're asking. In 2TT time they're asking. Either say 2TT time or they say, I mean, if they say let's suppose pure Aloha, then they can just say vulnerable time, because the vulnerable time in the pure Aloha is 2TT. So here the lambda is 2G. So which means that if you put lambda equal to 2G here in this formula, k is 0. So it will be e power minus lambda basically, right? So e power minus 2G. So this is your answer. And the same answer can be obtained if they ask you just like this. Let's suppose if they ask you something like this. Okay, if they say pure Aloha, don't worry, they will not be asking anything from pure Aloha, because no one is using the pure Aloha. It is even worse than slotted Aloha. We will see why. But still, just for the theoretical purpose, let's just have it. Okay, transmitted. See, here they say entire vulnerable time. So what is the entire vulnerable time in the pure Aloha? It is 2TT. Okay, so that's why the calculation will be same, because you need to modify the lambda. Okay, here also you are getting this answer, here also you are getting this answer. The reason being is that here they have said 2TT. That's why you are getting this answer. Here they have said just I mean they have said vulnerable time, which is anyway 2TT. Now suppose if they ask you this question. Let's suppose they ask you this question. They say this is not pure Aloha, this is slotted Aloha only. And then they say vulnerable time. Then what is your answer? Do you need to modify your lambda? Tell me, what is the answer you will be getting? Lambda will be just G, right? So probability of x being 0 is e power minus lambda, which is e power minus G. Okay, because the vulnerable time here is just TT, because it is slotted Aloha. Okay, so let's just see the questions. From this it will be more clear. So by the way, if I ask you the throughput of, see, the throughput of pure Aloha, then it is G into e power minus G. If I ask you the throughput of slotted Aloha, this is G into e power, this is G into e power minus 2G, this is G into e power minus G. And this slide is very, very important. Okay, this is, I mean, both the throughputs are in packets per transmission time only. The unit is same in both the throughputs, and this slide is extremely important. Okay, so very important formulas. I mean, you need to remember the throughputs. Okay, throughput in pure Aloha is this much. Throughput in slotted Aloha is this much, right? Okay. Now, throughput in pure Aloha is this much. If someone asks you what is the maximum throughput you can achieve, you just differentiate and get the zero. Then you will be saying that, okay, at G equal to 1/2, you are getting the maximum throughput. And the maximum throughput value is just 0.12. I mean, earlier it was 1 upon E. Now it is 1 upon 2E. Okay, it is 1 upon 2E. Earlier maximum throughput you could have got is 0.368. Here maximum throughput you can get is 0.183, which is extremely low, right? So it is saying that you can just I mean maximum 18% frames, that to maximum. Okay, maximum 18% frames can get successful transmission. That is also maximum. Okay, that is maximum 18% frames or success. So that is why no one is using this slotted Aloha. Right. So G value 1/2 is giving you the maximum throughput here. What does this mean? That in one slot, you are sending half frame, which means in 2 slots or in the entire bendable time, you are sending just 1 frame. Isn't it seem logical? Also, that in entire vulnerable time or in two slots, you are sending just 1 frame, right? And then you are getting the maximum throughput. So yeah, this is logical also. Okay. So this is the throughput, and the maximum throughput you will be getting at G equal to 1/2, and the value of the maximum throughput is 0.814. Okay. Now let's solve these questions. Now just forget about everything that we have seen. Don't worry, with the questions, the things will be easy. Okay, let's just solve the questions directly now. So what they're saying, a group of stations share 56 kbps pure Aloha channel. What is the maximum value of throughput in kbps? So the bandwidth is given to you. Bandwidth is given to you is 56 kbps. Now they're saying what is the maximum throughput that you can get in kbps? Okay, so they are using pure Aloha. So what is the maximum throughput that you can get in packets per slot? Do you remember? This was 0.18, right? 0.18 is the maximum throughput in pure Aloha you can get in packets per slot. So maximum throughput is 0.18. Okay, that is also basically, that is also the efficiency. This maximum throughput is also the efficiency. So if you want, I can just say that this is also efficiency, right? So you are just 0.18. Maximum efficiency that you can get is 0.18, right? So will the efficiency be having any unit? Will this efficiency be having any unit? No, right? So this maximum throughput and efficiency are same in the Aloha. Now, which means you are getting 0. You are just 0. Maximum you can utilize. So you can utilize this channel maximum 0.18 efficiency, with the maximum 0.18 efficiency or 18% efficiency you can utilize. If the bandwidth is given to you this, then what is the maximum throughput that you can get in kbps itself? Just multiply the maximum throughput you can get is basically you just need to multiply by the band efficiency and the bandwidth, right? So with pure Aloha, the usable bandwidth is just this much in kbps. Okay, so you can say the 0.18 this much, this is your maximum throughputs in packet per transmission time. Okay, so if they give you the packet length and they give you the transmission time, which means they give you the length and then they give you the TT. Okay, then can you calculate this in the kbps? Then we can calculate in the kbps. Okay, so instead of that, they have directly given you the bandwidth. So basically if they give you length, then what you will do, you will, let's suppose L equal to some bits. Okay, some bits, I mean the length is basically some bits. Okay, in the length is in L bits, let's suppose it is bits, and they give you the transmission time. Let's suppose this is in some seconds. Okay, let's suppose it is kilobits. Then from this packet per transmission time, if you want, then what you will be doing, you will be, for this packet, you need to convert, let's suppose, to the kilobits. Then you will say that you need to multiply the 0.18 into L kilobits. This will be kilobits per transmission time. You need to multiply by the L if they give you the packet length. Is this okay to everyone? I mean, you can understand in this way also. Okay, that if they give you that, okay, this is the length of the packet, then you can just multiply the length of the packet, and then you will say these many kilobits you are sending per transmission time. And the transmission time is also given, let's suppose, which is TT seconds. Then you will say that, okay, in 1 second, how much you will be sending? If in TT seconds you are sending this much, if in TT seconds you are sending this much, then in 1 second, we will be dividing by the transmission time or multiplying by the transmission time. In TT seconds, you are sending this much. And if I just ask you in 1 second, just divide by the transmission time, right? So you will be getting 0.18 into L upon transmission time. So this is basically in kbps. Now this is nothing but bandwidth. So you can directly multiply by the bandwidth also. Okay, I mean, this is just one other way to understand it. Little bit, have you understood this this second way, what I'm trying to say? This is the packet per transmission time. You just need to convert that to in kbps. So they have not given the length and transmission time explicitly. They have given directly the bandwidth. So you can directly multiply by the bandwidth. So because this is efficiency, right? This is efficiency. So you can directly multiply by the bandwidth, and then you can get your throughput. Okay. If they give the packet and transmission time separately, then also you can do it. And if they directly give the bandwidth, then you can directly multiply by the bandwidth, and then you can get your answer. Because packet, I mean, this length upon transmission time is nothing but the bandwidth. Okay, but I will prefer that you understand with the first way. Okay, which means this is the efficiency of the pure Aloha. And if the bandwidth is given to you, then you can say the maximum throughput in kbps. I mean, in packets per slot is definitely this, but in kbps, how much maximum throughput you can get? The maximum throughput you can get is basically bandwidth into efficiency, right? Yeah. So let's just solve this question. So what they're saying, that you consider the pure Aloha. Okay, the frame length is given to you is 1000 bits, right? This is the frame length. Now the channel transmission rate, which means the bandwidth is also given to you, is 1 Mbps, right? Which means 10 to the power 6 bits per second. Now the aggregate number of transmission across all the nodes, including new transmission and the retransmission, you will get to understand what is this retransmission in the next lecture, where we will talk about the back off. Okay, so you will get to understand this retransmission. So, but let's just see what they're saying. The aggregate number of transmission across all the nodes, including new frames, is modeled as a position distribution with the rate of 1000 frames per second. So, can you tell me what is G here? What is the transmission time? Transmission time will be length upon bandwidth. So I think it will be again 1 millisecond. So what is G? If you are sending 1000 frames in 1 second, then in 1 millisecond you will be sending just 1 frame. So G is just 1. Right? G is 1. From here you can see that G is 1. Throughput is defined as average number of frames successfully transmitted per second. In the frames per second, they are saying the throughput. So they are asking the throughput. So G is given to be 1. I think this is very easy question. So G is given to 1. Can you tell me the throughput? Throughput in packets per slot or the frames per slot? So it will be, in pure Aloha, the throughput formula in frames per slot is G into e power minus 2G, right? In pure Aloha. So it is 1 upon E square, right? If G is 1, then it is 1 upon E square. Okay, in pure Aloha. Now they're saying that this is packets per transmission time. Now they're asking, okay, so they're asking in frames per second, basically. Okay, they're asking in frames per second. So in 1 millisecond, in transmission time is 1 millisecond. In 1 millisecond, if you are sending 1 upon E square, then in 1000 millisecond or in 1 second, these many frames you are sending, you can multiply into 1000, right? And then you will be getting 135 as an answer. Okay. So 135 is answer here. This was very easy question. Once you know that how to calculate this G, what is this G, then you can easily calculate this, right? And what is the formula of throughput? And what is the unit of this throughput? So what is the unit of this throughput? This is frames per slot, right? Frames per slot. The unit of this throughput is frames per slot. And that's how you can easily calculate this question, easily solve this question, right? Okay. Now, let's just move to the next question. Okay. So maybe let's just move to the next case. I mean, if you remember that there are two cases. One is that there are infinite or there are many frames, many stations. But second case could be there are finite number of stations. Okay. So in this case, let's just see that how to analyze the efficiency of this case, right? Cool. So this is very, a small topic. Let's just understand this. So suppose that there are n stations, okay, which is finite here, n stations. And each station is sending with probability P. This P is the probability for the transmission, okay, transmission probability. Now, earlier, you remember, we were talking about G, right? Earlier, we were having G. What was that? This was, I mean, how many number of frames system was generating, right? System is generating in one transmission time, right? In one transmission time, something like that. So earlier we were having G. Now here in this case, we don't have G. In this case, we have individual probabilities. Okay, we say that, okay, P is a probability by which someone will be transmitting, right? Anyway, and let's just see directly analysis of the slotted Aloha. So here I am saying there are n stations, right? There are n stations, and each is transmitting with the probability P. So currently we are having the probability P. Earlier we were having G. Okay, we were not having individual probabilities. Here we are having individual probabilities. Now, if I ask you what is the probability that slot T is successful, okay, I mean, if a given slot is having the successful transmission, then it means any one of station is transmitting, any one of the station is transmitting, I mean NC1, and only one of the station transmitting, and rest stations, which means n-1 stations, are not transmitting. So with this much probability, this slot will be success, right? I will be having successful transmission with this much probability. Is this okay to everyone? So this is the probability of successful transmission. What was the probability earlier of successful transmission? Do you remember? In slotted Aloha, it was G into e power minus G. Okay, this was earlier. That slot will be having any successful transmission. Okay, that X is exactly 1. This is here. Now exactly one station is transmitting. This is the probability here. Okay, this is earlier. Right? Okay. Now, in case of okay, if you want, you can just differentiate it, and then you can check that, okay, for what value of P, what should be the value of P, such that I get this probability maximum. Then what is the probability? What is this P? And this is also throughput. I mean, the things are same here. Throughput per. Can you tell me what is the unit of this throughput? Packets per slot, right? Packets per slot. Okay. I hope you just understand this line. Okay. That's only needed here. This line only. Is this okay to everyone? Okay. So maybe I can directly tell you the questions. So let's solve this question. What they're saying, recall that nodes in the slotted Aloha transmit each with the probability, let's suppose P. Now suppose that given channel has exactly 8 nodes. Then what is the probability there is a collision in a given slot? Okay, so what is the probability there is a collision? Okay, what is the probability there is no collision? This means that no one transmit, probability no one transmit, or exactly one plus exactly one transmit. I mean, this case is actually very simple. Okay, you do not have any G and these things here. So let's just do this quickly. Okay, so what is the probability no one transmit? What do you think? The transmission probability is 1 minus p, then no one 1 minus p power n, right? Plus, or maybe 1 minus p power 8. Okay, probability that no one transmit. What is the probability that exactly one station transmit? Again, 8c1, okay, 8c1 into p into p power 1 minus p power 7, right? So this is the probability of no collision. They're asking probability of collision. So you need to subtract 1 from 1 minus this, right? So sorry. So let me just solve this on the next page. So you can see that 1 minus this quantity, right? Is this okay to everyone? I mean, that kind of easy questions only they will be asking. So let's just solve this PYQ. So what they're saying, let's suppose there are n stations in the slotted local area network. Each station attempts to transmit with a probability P in each time slot. Okay. Then what is the probability that only one station transmit? A is the answer or C is the answer? Yeah, A is the answer, right? Only one. If only one station transmits, this is the probability. If they say that okay, given station transmit, I mean, I do not care which one. I do care which one. Like the third station transmit, then third station transmit, this is the probability. Fourth station transmit, this is the probability. Fifth station transmit, this is the probability. Anyone transmit which is either third, fourth, fifth, which means it will be plus this. I mean, n times this much, right? Which is just this, right? So A is the correct answer. Only one station transmit. Okay, I do not have the answer, but A is the correct answer. Okay. Cool. So I think that is all needed here. Let's just solve 1 or 2 more questions. Probably you will get to understand more. So they are saying here that A and B are 2 workstation connected through printer. Okay, slotted Aloha they are using. A and B are having many frames awaiting access to L. Suppose A and B implement using the following strategy. Each will attempt to transmit with particular slot with the respective probability PA. So A sends with PA probability and they're saying B sends with PB probability. They are having different probabilities. If both transmit in the same slot, the slot is wasted due to the collision and the frame have to be retransmitted. So that the efficiency of this scheme is this. What is the efficiency? Efficiency means that exactly one transmit in the given slot. So what is the probability that exactly one transmit? Either A transmit or B transmit, right? So can you tell me if A transmit, then B doesn't transmit, right? And if B transmit, then A doesn't transmit. So if you check, if you just sum this up, it will be just same as this. Okay, you can just check it. PA plus PB minus 2 PA into PB. Is this okay to everyone? So efficiency is nothing but, as I told you, it is nothing but slot being successful or maybe slot not getting wasted, right? So these things, I mean, the fundamental idea is the same. Here, I just need to deal with the individual probabilities. I do not have G here. G is not here. Here we have the individual probabilities. That's all. Okay. Here we do not have G. Earlier we were having G. That's the only difference between this case and earlier case. Okay. That's all you need to know. Understood? So basically this is the G that you're getting. Oh, sorry, this is the efficiency that you're getting. Okay, cool. Now let's just solve this question. Maybe what they're saying, consider the slotted Aloha. There are 10 stations that are competing for a slot by transmitting with the probability 0.1 in each slot. So what is the probability of transmission? It is 0.1. Here you do not have G. You have the probability, individual probabilities of the transmission. They always have one packet to transmit, have packets to transmit. Find the average time it takes one station to transmit 5 packets. Okay, this is good question. So see, how many stations you have? 10 stations, right? What is the probability that there will be success? For any station, any given, okay, for any given station, what is the probability of success? Suppose I'm giving you the station. Do you need to have NC1 here? Will you be having NC1 here? You will not be having NC1 here, right? So you will say that, okay, I transmit, no one else transmit, right? So this is the probability of success for the given station. Which means just to transmit one frame, how many slots it will be needing? Can you tell me now? Can anyone tell me? To transmit one frame, how many slots you will be needing? Yeah. To transmit one frame, number of slots will be 1 upon P into 1 minus P over N. Okay. Now they are saying if you want to transmit five packets, then how much time or how much slots will be needing? On average, you will be needing these many slots or this much time. I mean, this much transmission time. So, so if they are saying that if you need to have five packets, then how much time you will be needing, or how many slots you will be needing? So for 5 frames, you will be needing this much, right? These many slots. That's all. That's how you can solve this question. Okay. By the way, from the Aloha, I think they have just asked 1 or 2 questions. This is one question, very easy question that they've asked. So this is one more question that they've asked. Let's just solve this question. And there is one more question that they've asked, which we have already solved. So I think this much, right? So they've just asked 3 questions. This question also was very easy. You just need to calculate G, and from then from there you can solve this question. The other question that we have solved was this much. This was also very easy question. But the last question is a little tricky. Okay, let's just solve this question. This last question is a little tricky. Cool. So before I solve this question, let's just solve this MIT question. So what they're trying to say, a group of n stations share some bandwidth is given to you. This is the bandwidth that you have. Each station has one packet arriving every 100 seconds, and packets are 1000 bit long. Okay, so in every 100 seconds, you have one packet. Cool. And packets are 1000 bit long. Now, what they're saying, what is the maximum value of n that the channel can accommodate? So let's just try to understand this question. They are saying that you can have this much bandwidth, right? This much bandwidth. Now, what is the maximum throughput? Maximum, the usable bandwidth that you can have, or the throughput, it will be in the slotted, in the unslotted, it is 0.18, right? It doesn't basically, first of all, it doesn't matter. These numbers are same. It doesn't matter whether this is a finite case or infinite case. Okay, these numbers are almost same, which means the maximum throughput in the slotted Aloha, unslotted Aloha is 0.18. So which means maximum usable bandwidth is this much, right? This much bandwidth you can use. Now, this is the bandwidth that you can use. Now they are saying, let's suppose there are n stations that you have. Okay, if there are n stations and each one is having, so this is basically in kbps. Okay, now if each one is basically sending 1000 bit long, one packet in 100 seconds. So which means 1000 bits you are sending in 100 seconds, right? If each one is sending 1000 bits in 100 seconds. Okay. If each one is sending 1000 bits in 100 seconds, then what does this mean? Then it means that you are basically, this is just for one. So you are sending, you can say in 100 seconds, you are sending 1000 bits. So in 1 second, each one is sending how many bits? 1000 upon 100, which means 10 bits. So in 1 second, each one is sending 10 bits. Okay, in 1 second. This is just for one station. For one station. Is this fine to everyone? So in 100 seconds, they are saying that one packet arriving. Each station has one packet arriving. And packet is 1000 bits long. So in 100 seconds, each one is basically having 1000 bits. So in 1 second, there will be 10 bits. Yeah. That is for only one station. If you have n stations, then what you will do? You will say n stations will be sending 10n bits per second, right? And maximum you can use, I mean, this is the available bandwidth for you. Maximum you can have 0.18 into 56 into 1000 bits per second. Okay, maximum that much you can use. I mean, this is the maximum bandwidth that you can use. So if there are n stations, then 10n bits per second that you will be having in the channel. And if the maximum that you can use is this much, then what is the value of n? So basically you can say that 10n must be equal to 0.18 into 56 into 1000, right? These many bits, that the maximum possible. So this 10n cannot be basically more than this. I mean, you can say it is less than or equal to this. So n will be, you can divide by 10, it will be 18 into 56, right? Okay, so which will be 1008. So what they are saying, that if you are having some channel which can have maximum of this much bandwidth you can use, right, in that channel. So how many stations that you have? I mean, how many stations that you can have in that channel? If one station is basically transmitting in 1 second 10 bits, so you can have this much. So basically this is you can say available bandwidth for you. Okay, this is available bandwidth for you, and this is the maximum. I mean, this is what is required. Basically 10n is required and this much is available, so n must be less than or equal to 1008. Now this question is also similar to that, so let's just try to solve this question. So what they're saying, consider a simplified time slotted MAC protocol where each host always has data to send. Okay, so what they're saying, that you are having a slotted protocol and each host has data to send and transmit with the probability p equal to 0.2 in every slot. So what is the transmission probability? It is given to you as 0.2. Now there is no back off, so we will see this back off later. And one frame can be transmitted in one slot. If more than once a host transmitted in the same slot, then there is a collision. Okay, what is the maximum number of hosts this protocol can support? If the host has to be provided minimum throughput of 0.16 frames per time slot. So for one station, they are saying I need to have 0.16 frames per slot. I mean, this much just one station will be generating. So n stations will be generating how much? N stations will be generating this much, right? Minimum this much they will be generating, n stations, right? In one slot. Now, what is the throughput of the Aloha? Throughput, if you remember, in this case, this is right. So in the slotted Aloha, this is the throughput. Now, this is the throughput that is given to you. I mean, that's what you know, that with this throughput, if you are having n stations, so let me use this capital N here also. If you are having n stations, then this is the throughput that you will be getting, or this is the probability of success, right? And what is the throughput that is required? Minimum this throughput that is required. Now you can see that this is np into 1 minus p power n minus 1, right? So 0.16 into n, this is the requirement. What is available throughput? Available with me, like I can at max provide, or maybe the available I have is basically n into p into 1 minus p power n minus 1. This is available. Okay. This is available throughput. And this is required to me. So whatever is required, like I can say that this available should be equal to, right? I'm looking for this throughput. So what should be the probability? Oh, sorry, what should be this n? The probability is given to you, which is 0.2, right? Yeah, 0.2. So this n will get cancelled out. And then you will say that p into, which is 0.2 into 0.8 power n minus 1 should be equal to 0.16, right? Okay. So what is the value of n you will be getting from here? See, you can just cancel this out. This will be 8 times this, right? If you multiply, yeah, if you multiply with 0.8, you will be getting this. So this is 0.8 times this. And then what is the n minus 1? N minus 1 will be 2. So n minus 1 will be 1. So n will be 2. Okay. So the annotated notes, I think, has been lost. Okay, somehow it got stopped automatically, and the notes has been lost. Okay, cool. So thank you everyone. Take care. Bye bye.